Okay, so what we're doing with fluid forces, remember we talked about fluids and all those characteristics. So what were some of the characteristics we talked about? What were some of the unique things about a fluid force? That perpendicular, it acts perpendicular to the surface. Linear increasing with depth. And it acts on an area. Okay, oh, somebody read there. God, we had good note takers then. Okay, and we talked about fluid pressure and how that changes. So we've got this measure H that we're measuring from the top of that fluid surface down. We're going to be using that as our kind of our guide to help us calculate that. But where we're going with this is we're going to be doing this on flat plates, and we'll be looking at it in curved surfaces also. What we're trying to do is create that equivalent beam load. Now remember, with our beam loads, we had a beam, and then we had some sort of a load that was expressed in terms of weight or force per length. So that's where we're going with that. And the way we get around that with the fluid forces is that we look at certain fixed widths. So we'll have this B characteristic that we'll be putting in there. And we put that B in there, and then all of a sudden we take out one of those dimensions, that Z dimensions there, and we can deal with it now like in terms of a beam force. So we'll consider looking at and this is probably something typical of our canal systems, where we'll have some sort of say for an example, a canal here, we'll have a water level up here. And we might have a gate down here that we're going to release water into the fields or something like that. And then we're going to use our characteristic measure there, H1 and H2, as our measure of the depth to those various points there. And then what we're going to do is just simply calculate those equivalent loads. So when we look at that gate by itself, what we're interested in is creating the load that's acting on that. And what we'll find is then there'll be a certain pressure here due to H1. And then when we get down here, it will linearly increase because H2 now will be bigger. And what we're going to do is, just like we did with the beams, just do a composite approach. Now, your author uses two triangles. I use a rectangle and a triangle, but either one works. What we're going to do is create an equivalent load here, our rectangular in this particular case, and our triangular, our that rectangular portion can be calculated by taking B, remember, so we're taking that fixed width, it might be a foot, it might be 10 feet, we'll figure out what that is, times the specific gravity. Specific gravity is now force per volume. So in a case of water, in our English system, 62.4 pounds per cubic foot. It'll be a little crazier, we'll do an SI example so you'll see how it works in the SI system. That H1, that basically describes how the water above it's creating all this additional pressure on it. And then we measure it then times that length there. So it's basically like we did there. It's just taking the area of this load area. And then the same thing with the triangle. Of course, it's half of that rectangular area there. The other thing to be very careful of is, remember, the triangle's this leg here. So it's going to be h1 minus h2. It's this portion of the leg because we've already accounted for this one in the rectangular portion there. And then finally, in terms of our moment equations, we're going to need lengths. Well, we know those lengths, basically. This will be so rectangular, it's going to be halfway. For the triangular portion, it'll be 1/3 up from the base. So that was the easy one. Now we're going to look at a little more complicated one. We're going to look at curved surfaces because when we look at dams and that sort of thing, basically, they're not always going to be flat on their surfaces. There's going to be some sort of a curve. And we'll just kind of talk about the approach. Okay, and I'll start drawing that over here, but let you write that down. So what we're going to do is create a free body diagram, basically of a certain volume of water that's around that curved surface. So a typical, the gate in this particular case might be curved now instead of straight, which then goes, geez, do I want to do a whole lot of integration? We can integrate that thing if we wanted to, but we don't necessarily want to do that. What we're going to do is create a free body diagram of this portion of the water here. So what we're going to do is kind of cut that portion of the water out. So my free body diagram of that portion of water looks like that. And where's my... Okay, second step. So we're going to create a free body diagram. We've cut that out, basically. We've cut it away from that gate there, and we're going to look at what that water is doing to that gate. Okay, so what we're going to do then is we're going to now substitute. We've cut this out, but we've got to think, okay, when we cut this out, there's going to be forces acting on this. When we think about this top surface here, this horizontal surface here, well, we've got all the weight of this water, this whole H1 of water acting on that. So in terms of what we're going to see here, the water sees this load of H1. So I've taken that portion of the water away, but I have to substitute in, like we do in equilibrium, that set of forces that are acting there. Same thing with the vertical cut, except now it will have that linear aspect like so. But again, we've taken all this water away here, and this is what that water is doing to this hunk of water here. So we've substituted that force in. The final piece then is then we have to find the CG and include the weight of that enclosed volume. So that's something we can do, hopefully, if the curve is something that's nicely defined, like a parabola or a circle or something like that, we can basically just go to the back of the book, grab the CG of this area, or the centroid of this area, and since we made the assumption that it's going to be the same material, it's water, gravity will be acting on it, so the CG and the centroid will be the same location. And then the final step we actually go back to equilibrium. What we're going to do then is say, okay, I've got all of this here. What I'm going to find then is to keep this all, this is pushing down, this is pushing this way, this is pushing down. There's going to be some sort of a single resisting force that I can calculate. And this goes back to finding, we can find the force and couple and then move that force to the single force location there where the couple goes to 0. What we'll have is then a single resisting force there. They're killing me. Okay, so what we're saying there then is that the resultant force of the water, in other words, we solve for this in an equilibrium sense. What we're saying then is that if we think of this as a two-force system, well, that force has to be equal, opposite, and collinear. So all of these forces will end up like a force like that if we resolve them all together into a single force. So this is the force we're not looking for. We're basically, when we design our gate, we're going to be looking for the force going this way. But it's just going to be basically equal, opposite, just in the opposite direction there. So it isn't as complicated as it looks there. It's just that you're going to have to keep all of these pieces together. Probably the most complicated part of that particular approach there is just finding that single resultant force. What we want to do is find that single resultant force, realize that basically if it's a two-force system, then the water will be acting in the opposite sense there, but equal, opposite, and collinear. So what we want to do then is to be able to start solving some problems. So we'll take a look at the handout that I gave last week. Does everybody have a copy of that? Did they bring it with them? I got a couple extras, but sure.
So that resultant there, is that going through that line of action? Is that going through like the radius, or is that going through that center of gravity?
It won't be going through, it may not.
It might not.
Yeah, no. It will find its own location, so there's no rule that it has to go. The only thing that goes through the center of gravity will be the weight of the water. That's the only thing we need that for, is just to figure out where that weight component's going. But when we find that resultant force or the resisting force, that single resisting force, it could be basically anywhere. Good question, though. Oh, sir.
The resultant is from the water force on the gate, is that what it is?
Yeah, so what we did is we solved for the force that basically resists all of this, right? Because this one's pushing down, this one's pushing over, this is pushing down. So I'm going to have a force that's kind of going this way, and we know it's going to be going up, right? So when we resolve it to that single force, we're saying, okay, that's the single force that's going to keep all of that in equilibrium. What I'm saying there is then, if we think of it as a two-force system, the water then is presenting a force in the opposite, equal opposite, and collinear direction there on the gate. So this is the force we want to use in terms of solving it, although even if you use this one, you just switch signs, basically. It's going to be the same direction, magnitude, and everything. It's just simply the sign's going to be different. But this is the one then that's acting on the gate, and then we do our calculations in terms of moment calculations, and we'll kind of see that when we go through this example problem. Any other questions? Everybody got this? Okay, so what we've got is a gate system here, and again, it's at depth, so it's going to be some depth there. It's point A there is at 0.45 meters down. Point B is an additional 4.8 meters down. The gate has a width like this, and then basically what there is a cable on this that's attached to a pulley there, and you're going to be pulling on that, and we want to figure out what force is going to be needed on that cable to be able to just open that gate. And the gate itself is 5 by 0.8. Anything else we need? It's water. That's another thing too. In the EIT exam, don't assume everything's water. Read the problem. Because they'll have some examples with oil or glycerin or something like that with a different specific weight. And you'll need to make sure you use the appropriate specific weight. That's pretty much it. So it's resting on a stop there and that sort of thing. Okay, so we'll get some general info out of the way there. So the density of water, this is all an SI note, so it's in meters. We'll be doing things in terms of newtons. So this is density. Our width is going to be the 0.5. And one way to check that then is note that we've been given the horizontal distance and the vertical distance there of that gate between A and B of 48 high and 0.64 in the width there. When we do the Pythagorean theorem, basically we find that our length then is going to be that 8. So the 5 by 8, then we can go back and say, okay, well then my width has to be that 0.5 meters. So that's how wide it is. We're going to use that then to take out the volume, that area basically, and bring it down to just basically being able to do a beam problem. Okay, so my depth to my first point of interest there at A is going to be 0.45 meters down. And what I'm going to do is then calculate what the equivalent beam load would be there. So my WA would be this. Now the one tricky thing to note here, B is my width, so I'm getting rid of that basically and bringing it down to now a linear load. Rho is my density, but this is my specific gravity here. So in the SI system, since this is kilograms, that's not a load, right? That's just basically a measure of mass. We have to multiply it times that acceleration of gravity there to get my specific weight. So that'll change that into specific weight. And then based upon knowing our linear theory there of fluid forces there is going to be that HA, or the distance down there to that. And then just simply plugging in those pieces there. Question?
It's kind of hard to tell in the picture, but where would the H of A be? Would you include? Why don't you include that 0.27 meters?
Does it not show the water level at that 0.45 the same line there? If it doesn't, write that in basically, because it shows it in mine, but it may not show it in yours. Is there a copy of? Okay. Well, at the 0.45. Just draw in a line there and say this is the water level if it didn't come out through.
0.45?
Huh?
At the top of the 0.45?
Yeah, at the top of the 0.45. So it's 0.27 down from C is where the water level is.
Okay.
So that's why that line's there.
And if there's a line on the left side of it too.
Yeah.
There's a water.
Yeah. So 0.27 is basically the height to that pulley. So, which kind of makes sense. Basically, we probably want to have it out of the water and not soaking in the water there. Okay, so when we get done with that, we end up with 2,207 Newton per meters, which is, again, think about it, our beam load, force per length. And I'm just going to convert it into kilonewtons there so we're not carrying around really large numbers there. And then the depth to B is going to be the combination from A and then that additional 0.48 or 0.93 meters down. And I'll skip putting in the, for brevity's sake here, the units, but usually you want to keep track of those units and make sure you're not doing anything messy there. But basically then, what we find then is that our beam load is going to increase from 2.2 to about 4.5. Question?
There are 3 meters in the parentheses, and there's a meters cubed on the bottom. Why is there an extra meter left over on the newtons per meter?
What did I do? Oh, yeah, that's a good question. Well, I think it has to do with this thing here. Somehow we don't lose a meter in that one. Because we get one there, we've got one there. Let me look at that one. I think it's this piece here that doesn't fit very nice. The SI system's not real happy about that.
What is that unit, right? Would the weight be a force? So it would just be a you have Newton over meter, it wouldn't be just Newton.
Yeah, like just kilonewtons.
Yeah, it'd be Newton over meter.
Or just over
Well, you're looking for weight, which is force.
just force.
We're looking for force, which is newtons, right? We don't want it in kilograms.
Yeah, but we don't need the meters, right, for the force?
Hmm?
We don't need the meters, do we, for force?
Yeah, we do, because what we're trying to do, remember, we're trying to get it into that equivalent beam load. So it's going to be a force per length, and then we're going to go across it like we did with the distributed load and
Yeah,
beams.
no, I understand. I don't understand why they're not, like, why they're canceling out, but yeah, I don't understand why they're canceling.
Was it because the base second squared goes into the Newton? That's why it was part of the Newton's.
Yeah, I've got to look that up. I can't remember, but there's something about this conversion here that doesn't.
Oh, that is what it is. That is what
We
it is.
need the base.
That's right.
The base is this length, which we don't necessarily need this.
This base?
Yeah.
Yeah, we need that because basically we got this area, and what we're going to do is we're going to take that out. We're going to say that's fixed. Okay, so then we can look at the beam, or it'll look like a beam, the plate will look like a beam at that particular point in time, and then we can do it with our two-dimensional centroid analysis.
It's because the Newton comes from the kilogram times meter per second squared, and then the other meter squared will cancel the meter cubed to a meter, and that's what I wanted.
Yeah.
It's the second squared.
I'll look that up and see if I can find a write-up, but yeah.
The kilogram times meter per second squared is actually a Newton.
Right.
So then after that's done, then you only have.
Yeah, that's why I say I think it absorbs that in terms of that conversion there. So we actually don't really see that one because when that goes onto that, it just creates the Newton. Yeah. That's the messy thing about the SI system.
Second squared. Second squared is Newton.
Yeah, it's second squared. So it's meter second squared. That's your acceleration of gravity. But multiplying that then times the kilograms creates a Newton. Okay, well, let's finish here. So we've got that. So going back to your question there in terms of why do we want it per meter, this is what our free body diagram is going to look like now. That's supposed to be straight. Now what we're going to do then is, crud. Substitute in that pin force there. We've got on there A is a pin. We'll set ourselves up a coordinate system like so. And this is what our distributed load will look like. So what we've done is simply with that B, and that's why we want to take that B into account there, is we've basically taken that dimension out of there, and we've created what looks like a beam load, something we can deal with now in terms of our statical equations. Now, of course, distributed load, we don't know how to deal with that, basically. We're going to do our equivalent load scheme there. I'm going to create equivalent loads to those two particular load areas. In this particular case, the rectangular and the triangular. Again, your author uses two triangles. Either one's fine. I don't like dividing by 3 2 times, but whatever works. And actually, it's a good way of checking your work.
So did we just move the weight from like the tanks on the side to like above the hatch? Is that what happened?
So your question is? Okay, so what we have is this, I've got to draw the picture here. We got this little thing like so, right? So this is my gate, right? It's sitting there kind of at this weird angle. So this is the gate. This is going to be my, I'll put in my dimensions there so we can see it. Okay, so what we've done is we've modeled that, and again, taking the fact that we know that the load is going to be acting perpendicular to that, it's going to be acting perpendicular to whatever angle that particular plate is at. So it's acting perpendicular, it's going to be acting at this angle. Now the nice thing about perpendicular is when we get into moment equations, it'll make it a whole lot easier. We're not completely finished with our free body diagram, because the one other piece we want is this cable FBC. Now, we could, when we think about it, if we don't have any sort of cable, if that cable doesn't have any tension in it, we would have a force there at B basically resisting that. But what we've been asked now is, okay, what is the force of that cable just to open that thing? So at that point in time, when we get to that point where it's just opening, B is not going to be providing, that little penstock at the bottom there is not going to be providing any force. All of the force of that gate, due to the pressure of that, will be going into that particular cable there. And the one other bit of information then we're going to need there is going to be some sort of an angle that we're going to need to calculate. And actually, we'll just get that out of the way right now. And that's why we have that point 27 there. That's why we needed to know where that pulley was, because we need to know basically the direction of that cable there. So this is now my free body diagram, of which now I can go ahead and the question I've been asked is, okay, what is the tension in this cable to get that thing to open up? So now I just simply go with my equilibrium equations. Oh, before I do that, though, I've got to figure out R1 and R2. Questions? Something not clear?
No.
Oh, you got it? OK. Okay, so R1 is just simply going to be this rectangular area here. So it's basically going to be this height here of 2.207 in kilonewton meters times the length of that particular gate, which is now going to be 0.8 meters. Multiply that, the meters will cancel out, and what we get then is what we want is the force that's acting, that R1, that's the equivalent force of that rectangular area there. And we're going to be taking moments from A because there's two unknowns there. And basically, all I really want is this force here. So I need to figure out where that's acting. Well, it's rectangular area. We know it's acting at the halfway point. R2 and D2. Okay, so again, don't forget that the rectangle here is always going to be, if you've done it via the rectangle, then you make sure you're actually doing that base leg. I guess that's why the author likes the use of the two triangles, because you're always going to be using both of those as the base of the triangles. But don't forget to add that little point there. It'll be just a little less than 1 kilonewton. And then again, I'm going to be taking my moment from A there, so it's going to be 2/3, since it's 1/3 up from the base of the triangle, or 2/3 down from the top. Everybody got this? I'm going to keep that up because I want to keep the picture up. Oh, okay. Let me know when you're done. Sir?
Can you explain the 2/3 one more time?
2/3. Okay. What I'm wanting to do is measure from A. I've decided in my head I'm going to be taking my moment at A, because that eliminates AX and AY. And the one thing I'm really after is this B, the force of BC. So I'm going to be measuring my moment arms from here. Well, in terms of the triangle, centroid of a triangle is 1/3 up from its base, right? Or 2/3 from the tip. So I'm just looking the other way. Good question, though. Good question. Make sure everybody understands. Can I do this now? Yeah. There's no size. Actually, why am I doing this in red? Let's purple. Okay, so I've drawn my free body diagram. The next piece is my equilibrium equations. Pick a direction in terms of what I want to consider positive. And again, the nice thing about what we're going to find about fluids is since they act perpendicular, distances are already measured perpendicular, basically. So it's going to be rather simple. Our rectangular area and we think about A there, it's going to want to twist me via right-hand rule in a positive sense, as will the other portion of the water. So that's my two components of water. Again, I could resolve them to one, but at this point in time, equilibrium is much easier in terms of just simply adding the extra term, instead of spending all that time creating a single resultant. Okay, so the next piece is going to be this cable. And realize that at this particular point there's going to be a horizontal and a vertical component there. So the vertical component will be the sine of that particular angle there. And then the vertical distance across there is 0.64.
Is that what you would want to do it though? Because wouldn't you want to just get the perpendicular component and then the other component that's that's parallel? Then you only have one. Because you're doing like X and Y components.
Uh-huh.
You could just do, doesn't that break it if you use basically line B as your axis?
Oh, yeah, I see where you're going. Sure, you could do that. You could rotate the whole system that way. Yeah. Mm-hmm. So basically take that force, but you'd have to create a component in this direction and then a component in the perpendicular direction. Is that what you're suggesting?
Oh, yeah.
Oh, yeah.
I thought that's what you were going to do. Never mind.
That's one way of doing it, yeah. Very easily. I just chose it because that was the convention I had. I set up my XY convention that way, but yeah, you could easily set it rotated there to that same system. The only trick there is then you'd have to think about, okay, what is the angle of that perpendicular there? I chose not to do that, but the other reason I like to do this in this particular format The reason why I like to do that, though, is just to keep pounding into you to think about those directions. When you think about the direction of this FBC, the way I have it drawn there is that's the first portion. The vertical portion is going to create a negative twist about there. Whereas you think about the horizontal force, it's going to create a positive twist there. So another reason I like doing that is just, again, let you think about how that twist is acting. It's a separate system that we have to keep in mind there. And there's always going to be tricks like that in terms of EIT exams and stuff like that, where one's going one direction, the other's going the other direction. And I'll guarantee you, they will on the EIT exam have it going both directions. I'll have an answer going both directions there. So again, think about that. Once you get done with that, very quick calculation there. We find that it's a little less than, for about 3.5 kilonewtons basically is all the force I need to do to put on that to pull it up. And as Forrest Gump would say, that's all I have to say about that. So you have a nice example of a curved surface example in your book. I'd suggest go take a look at that. To be honest with you, when it comes to exam time, I'm not going to do a curved surface. So you won't have to study that. I'll put that on the notes when we get to that particular point there. But I want you to be able to do a flat plate. You really need to be able to do flat plates and that sort of thing. Curved surfaces, way cool method of doing it, but a lot of work to get there. Okay, so we spent our time basically with all of these particular problems in the 2D world. Even though fluid surfaces really are 3D, we resolve them down to a 2D problem by taking account of the fact that we can take that width out of the problem there and give ourselves basically what looks like a beam example. But there are going to be problems now where we have to do some 3D stuff. But what we're going to find is it's pretty simple. Basically, we're just going to include the third dimension there. So
So we're looking for the centroid 3D space, the 3D space. Are we going to, for this class, are we going to be using like double arrows and triple integrals?
that's exactly where I was going. Okay, you've led me right into it. Yes, there's an integral approach and there's a discrete approach. We're not going to be doing triple integrals and stuff like that. Just to let you know it exists, and if you really like math and that sort of thing, or you got a math friend or something, you can have them do that for you. What we'll be concentrated on is the discrete form most of the time, yeah. And any sort of thing you'll see on the EIT exams and stuff will be discrete. They're not going to have you do a triple product. But just to let you know, it comes from that. You can do that. If you really love math and that sort of thing and calculus, you can have at it. And I'm sure there's some curved surfaces out there you can do. So we'll be concentrating on the discrete form. I guess it's St. Paddy's Day. The green doesn't want to go away. And recall, going back to the question that we had a little earlier there, we had these assumptions. Gravity acts equally. Well, most of the sizes of the products and that sort of thing, and the things that we're looking at, there's not going to be a situation where the gravity is going to be acting differentially on it. But you know, when you get into, some of you guys might design space stations and stuff like that, so there may be issues at some point in time where you need to think about that. Just understand that's part of it. And then if it's a uniform density, so it's not some composite type thing where you've got, you know, metal and steel like reinforced concrete, where you've got steel and concrete going on, but if it's the same sort of stuff, then it goes back to that question, is a CG the same as a centroid? That's the case when it is. And the nice thing about the centroid then is then we're finding the centroid of a line or an area or a volume. And it doesn't have anything to do with material properties. We don't have to go look up, you know, whether it's steel or concrete or anything. The centroid will be acting at the center of gravity will be acting at the centroid there if it meets those two assumptions. Okay, so we'll go on to our example. Oop. Didn't get rid of that example. Okay, so we're going to we'll look at a problem here where we've got a set of wires basically. So we're going to look at this again in the discrete form. Again, if some of you really want to integrate it, I'm sure there is a way of doing it. But again, this might be some mobile you're putting together for your grandson or something like that. You're going to want to figure out where to put that wire so the thing isn't flipping around and that sort of thing. And what we're going to do is find then the centroid of that particular volume now. And even though they're lengths, it's still going to be a particular point in space that we'll be looking for. And what we're going to do is attack this the discrete form, using the discrete form there. So we're going to be looking at breaking these up into linear pieces there. The nice thing about the linear pieces, we know exactly, since it's the same thickness throughout, that things will be acting at the center of those particular pieces there. So center of gravity, knowing it's made of thin brass rods of uniform diameter. Okay, so we'll be using the discrete form. Now notice most of those pieces we actually know the length. The only one that's going to be a little tricky and the only one that we're going to need the length for there in terms of that's a little out of whack there, and we'll just use Pythagorean theorem there basically for the three edges there. Square them, take the sum them, and then take the square root. And what we find then is that length of 1.84. Now the length is important because again we need to know exactly how much weight is going to be in that particular piece, so we need to know basically its length. Then at that point in time we'll just simply put together the pieces. So we'll set up a table. First thing we'll talk about is the pieces. So that's supposed to be piece. And then what we're going to do is just assemble all the pieces that we're going to need to do there to assemble this thing. So the length we just calculated. Okay, and then what we're going to do now is look for those individuals. So we're going to be looking at that one piece there. So we'll draw it up here a little bit.
It's going to be 1.5. Data. You put 0.6.
The z direction is 0.6, right? So we're going from A to B. So A is going to be 1.5 up, and then B will be 1 and 0.6 over, right? Does that make sense? Okay. Oh, did I? Okay, did I do it the other way? Sorry. Okay, so now we've got 1.9.
Batteries are probably dying in your calculator.
That must be. I was going to say. Well, okay. Well, let's just put it at 1.9. 1.9. That sounds like the author too, doesn't it? He's always pretty cool in making sure. Okay. So I might need to calculate. Keep your calculators handy here, folks. Okay, so now what we're going to do is okay, we're looking at this piece AB. What we want to do now is find the local centroid of that particular piece. Now, because it's at an angle there, the nice thing though is again, since we know it's a straight piece, we know that the center of gravity of that particular linear piece is going to be in the center. So that center is going to be now in the x direction instead of 0.6. X direction, that'd be 1. It'll be 0.5, right? So this end's 0. This end goes all the way out to 1. So this centroid of that particular piece will be 0.5 in the x direction. Comfortable with that before we go any further? And then we have the y direction. What would that be? 0.75. Z? 0.3. Okay? And then what we're going to do is put together our columns that we're going to be adding up. So it'll be XL. Oh, and somebody calculate that one for me then, since, no, this is, yeah, you guys are going to have to calculate this for me then. So 1.9 times 0.5.
0.95.
Okay, y bar L will be 0.5.
1.425.
That sound right? Oh, 0.75, right, okay. Okay?
0.57. You mean ZL?
ZL, thank you. My batteries are running low. Okay, that's piece 1. That's the most difficult one because we have to figure that out. The other ones are all nicely arranged on axes. So our particular piece BD, so BD is this piece here. I'll be looking at the centroid of that one there. So I describe the centroid there in terms of the little x, y, and z centroids there. Then simply multiply that out. Nice thing, we get some zeros in there. DO will be a length of 1. So this will be this one here. And then the location of the centroid there is a pretty easy one there. It's just going to be 0.5 down that x-axis, because it lies on the x-axis. And those two terms will then zero out. And then the final one is O to A. And again, it's on the y-axis, so it'll be halfway up. And then I fill out my other terms there. And then the four columns essentially I need to sum up will be these pieces here. So this will be 2, 5, 2, 3.1. So it'll come out to 5, huh? Sounds like the author, nice and simple. Someone want to add this one up for me here? So we got 0.11. 1. 25.5. 2 point what? 55?
Right.
And then this final one here. Okay. And then in terms of finding the combination of the whole system then, is just simply the summation of those columns there. So it's going to be that piece there with the local discrete pieces of their lengths times their moment arms, that basically first moment of area when we think about it in terms of our equivalent system there. And this one will be, let's see, 2.05 over 5. Run that one for me. Should be about 0.4. And that's
0.51.
.15. Okay, so what we've done then is found the centroid of that particular combination system there using the discrete form. This is the form you'll be used to in terms of 3 dimensions and stuff like that. We did it with lengths. You can do the same thing with areas or volumes and that sort of thing. You'll be constructing tables basically the same way and just using those first moment of area type. This is first moment of length there when we think about it, but basically it's just a simple application of that. Question?
So we were just using like the length instead of the mass because it's uniform?
Because it's uniform, exactly. Yeah, so we can take advantage of that. If it's different sizes than everything, then we're going to start looking at the volumes and stuff. 45? Okay. So basically, if you look at just that single point there, you have two unknowns, right? So you can solve for that. Sum of forces x, sum of forces y, you're all done. Or you can do force triangles. I put both of the solutions on. So the solution for that problem is there. So I want you to learn from it. So there's two different approaches using the Cartesian system there. And then I've also used the force triangle. So go look at it, get comfortable with it. You might see it in the final, something like that. But the key thing is we can solve for this force, which was TCD, I think. Or no, this is BC. This was TCD. Once we solve for that one, then we can come back to this one, which was everybody's favorite, the 3, 4, 5 triangle. And this was at 45 degrees. So this was TBC and TAB, and then our unknown W. We solve for that one, so we just use Newton's third law, right? Come back here, realize that if this one's going this way, then it'll be going that way in this particular problem here. We have two unknowns there. You can solve for W then. So I apologize for those of you that were freaked out there, but it's going to be something you're going to need to be able to solve in the future. And
3, 4, 5 triangle, how would you just do like law of sines or something to find that angle right there? Or what would you do?
you can do, yeah, you can do that. But the nice thing is remember what sine is simply a ratio of the long length over the far distance there. So it's like, so basically, oh, actually the other way around, sorry. So sine is just simply, so instead of, the reason why they like to do that is then when you consider the horizontal aspect of TAB, say for example, it's just simply going to be 4 over 5. And you don't have to go through the angle calculation. So that's why people like that 3, 4, 5 triangle. The other common one you'll see is a 12, 13, 1 or 12, 13, 5 angle. So basically, it's just noting the fact that sine and cosine are just simply ratios.
Shouldn't it be A over L?
Oh, crap. My batteries are running low. A over, thank you. And then cosine is simply going to be the B over L there. So it's just a nice little trick to know, especially when you're doing EIT exams and stuff like that, because you don't want to go through and then calculate the angle and then throw sine at it. You're doing two separate things there if you recognize the fact that it's just simply those ratios. So those will be very common. It'll be the 3, 4, 5, and then I think it's 12, 13, 5 is another one that you'll see a lot too. And there's some other ones too, but those are the two most common ones I've seen. Okay. The one good thing I really like to see that I liked in terms of the exam is everybody did well on the three-dimensional problems. So you guys are you're up to snuff in that. I'll go ahead and put them out for you to pick up. We'll go ahead and call class a little early today. I will hang around if you want to go through the problems. We can meet across the hall there and discuss some of the problems. They're in alphabetical order. For now.
One of your homeworks, I think it cut off part of the problem. It's supposed to be 10 millimeters, and it looks like it says 10 meters on one of the homework problems you put up. I found it online, so it was like the same problem. Because at first I thought all it shows is 10M. When I looked at it, I'm like, man, 10 meters thick, that'd be like really, really thick.
Is it the one we're working on now?
It's like 8A or B.
Out of 65, right?
Out of 65, yes. Out of 65.
You're talking about the missing problem, or
It's not missing.
Yeah,
It's part of the
half
homework
of
is
it's
cut off.
Yeah,
Yeah, this one right
Oh.
here, it's cut off like
it's right here.
right
Yeah.
here.
I was just about to tell you that I wasn't able to do my homework completely because of this.
Oh,
I think it's supposed to
okay.
be 10 millimeters. Because I found this problem online. Because at first I'm like, 10 meters, that doesn't seem right. And then when I did it the first time, it was like really
Let me
weird.
see. I see what I solved.
Oh, yeah, it's
So you're
missing.
using 0.01 meters.
It's missing it's millimeters to determine it.
And it's cut
Yeah.
off a bunch of stuff. It doesn't say density of, it doesn't say determine.
I was just about to
And it didn't
tell
say it
you.
was a pin, but you can kind of infer all those things. The only thing was, at first I thought it was 10 meters. And I'm like, what the heck? That's right.
Wow. Okay. Oh, great. Thanks for bringing that up. I'll have to fix that then.
I was just gonna tell you because you know how to turn in the homework. So Thursday, like I was gonna tell you I didn't finish that problem because it was incomplete. So I made a note of it on the homework. I said it was incomplete.
Okay, well, we'll just have to punish the instructor on that one then. We'll take off points on the instructor. Okay.
I was just gonna tell you about that too because you know I gave you my homework for Thursday. And
Okay,
I was gonna say
okay.
I couldn't complete.
I'll make a note to the grader that's right. Actually, though, most of the other folks, I'll grade yours maybe separately, but most of the other folks I can get this out to them before because we still got a few more days. Okay.
Yeah, because I wasn't sure.
Let me work on that
I
then.
wasn't
Yeah.
sure. I was assuming that must be density, but I was like I don't know if that's 10 meters or.
Yeah.
So I was like I don't want to stress out and like do it wrong, so I just like left it. I let it be.
Okay. We'll talk about it then.
Okay.
Sir.
So I was marked down for a free body diagram. I just wrote my arrows onto the diagram itself.
But I made an important point in class that it's got to be separate because when you put it on that, it's hard to see and you can't tell and you'll be missing forces and stuff like that. So I really insist on a separate free body diagram.
Okay.
That's pulled away.
Okay.
That's what I meant by separate. Take it away from this because this is all jumbled up and I'm not sure exactly what you mean by a force this way and that way. I could kind of infer some stuff. If you want to argue it and stuff like that, I'm trying to think, did you do the rest of the problem?
I did the whole problem.
Well, you missed
I just,
a couple
I
of
missed
little
that
things, yeah.
little bit. I just didn't separate it from that.
Yeah.
I didn't want to take time to redraw it during the test. And
Well,
it
that's
messed
what
up
I'll.
on the transfer.
Yeah, I was going to say I want you to do, but other professors are going to want you to do too. So
Yeah,
I'm giving you a heads up too that when they want a separate free body diagram, they want a separate free body diagram.
Gotcha.
But
Still see.